In this video, we'll begin discussing a sequence, and specifically an infinite sequence. So an infinite sequence is going to be a list of numbers written in a definitive order. So A1, A2, A3, so on, and then maybe a general representative A sub n. And this sequence, notation-wise, will typically be denoted as just that general representative A sub n within curly brackets. Or to specify that it's an infinite sequence, we might also join that with an n equals 1 to infinity. So let's look at a motivating example. A sub n equals 1 over n. So if we write this out as a list, when n is 1, we get the number 1. When n is 2, 1/2, then 1/3, 1/4, and so on. The general representative is 1 over n. Now, a nice thing to notice here is that we can also think of a sequence as being a function, but specifically the domain would be inputs which are natural numbers, which are positive whole numbers. We plug into the function 1, 2, 3, 4, and so on. So we can really think of representing this graphically. So associate it with each one of those positive whole numbers. You have the output for your sequence. So A sub 1 would be the output associated with 1. A sub 2 would be the output associated with 2, which is 1/2. Then with 3, you would have A sub 3, and so on. And note here that there's an associated function that each one of these points lies on that curve f of x equals 1 over x. And the biggest, most natural question we are going to investigate it related to sequences is when n is large, i.e. when we're further out in our list of numbers, what are they approaching? What are they becoming close to way to the right? So we say that a sequence has a limit L, and we use our standard notation, the limit as n approaches infinity if A sub n is equal to L. If we can make the terms A sub n as close as we would like to L by letting the n be large enough. So in terms of a graphical representation, thinking of the sequence plotted out as points, we see two visualizations of a sequence having a limit L. That is, the further you get to the right, the closer those individual points are getting to that value of L. So if we go back to our motivating example with 1 over n, if we want to know what the limit is as n approaches infinity of 1 over n, note that the n value that we have in the denominator is going to infinity. And 1 divided by something big is something small. So exactly as we saw visually on our previous slide, the limit of the sequence 1 over n is L. So in this case, we would say the sequence converges to 0. And if the limit did not exist, the language would be that the sequence diverges. So let's determine whether the following sequence converges or diverges. And if it converges, find the value of its limit. So just by visual inspection, what we might note here, 5n squared plus 1 all over 1 minus 2n squared. So this is rational in n. The degree in the top is equal to the degree in the bottom. So our past intuition tells us to just divide those leading coefficients. That is, we should end up with minus 5/2. Let's go through the work and maybe see how we would go about this. So we would like to calculate the limit as n approaches infinity of the sequence 5n squared plus 1 all divided by 1 minus 2n squared. So what we're going to do is just multiply by 1 in a fancy way. I'm going to note that the largest power of n in the denominator is 2. So I'm going to multiply by 1 over n to that power, divide it by 1 over n to that power. And if I take the 1 over n squared and distribute it through the top and distribute it through the bottom, we'll have the limit as n approaches infinity of 5 plus 1 over n squared, divide it by 1 over n squared, minus 2. And thinking back to our previous experience with limits, the most natural thing to do at this point would be to take that limit and kind of distribute it through, the limit of the top over the bottom, and then break it up respectively. So that would be the limit as n approaches infinity of 5 plus the limit as n approaches infinity of 1 over n squared, all divided by the limit as n goes to infinity of 1 over n squared, minus the limit as n goes to infinity of 2. And individually, these are all limits we can evaluate. The limit of a constant should always be that constant. As n goes to infinity, 1 over n squared goes to 0, because dividing by something big gives you something small. So as claimed, the value of our limit is minus 5/2. So we would say in this case, the sequence a sub n converges to minus 5/2. So note in this previous example, we've kind of made the assumption that our basic properties of sequences, or limits that we've seen in the past, will be true. And just to put your mind at rest, let me assure you that they are. If you have two sequences that converge, and c is a constant, all of our basic limit laws still hold true in this situation. You can break up a limit over addition and subtraction. You can pull constants out of limits. The limit of a constant should always be that constant. And you can break up a limit over multiplication and even division as long as you're not dividing by 0. Furthermore, as we're going to see, you can take a limit and move it inside a continuous function. And here what we're trying to suggest is that you can move it inside powers, so that would even include square roots. Another property is that we've mentioned there's this related function for the sequence. And recall from our motivating example, we had a sub n equals 1 over n. And how we find this associated function is we take our sequence and we replace each n with an x. And it turns out that if the limit as x goes to infinity of that associated function exists and is some number L, the same is true for the sequence. Now, why is this helpful to us? Well, the big reason that it's helpful is when you're dealing with limits of the form here, as x goes to infinity of f of x, this is a situation where you can apply L'Hopital's rule. Because in order to apply L'Hopital's rule, you need a continuous differentiable functions, whereas when you're dealing with a sequence, you just have a list of values, which is not something you can differentiate. So if you ever want to apply L'Hopital's rule, you need to rewrite in terms of the associated function. So for example, if we look at the sequence a sub n equals L sub n, natural log of n over e to the n. So remember, just an infinite list of numbers, but the observation here is if we think about taking a limit as n goes to infinity, a natural log over an exponential, you would say for big values of n, you expect a natural log to go to infinity. Similarly, for big values of n, you expect an exponential to go to infinity. So in order to take that limit, what we would really like to do is use L'Hopital's rule. But we can only use L'Hopital's rule if we rewrite it in terms of a function of x. So we need the following work. So we're starting off with the limit of the sequence, and we can immediately rewrite this in terms of the limit of a function. And I know this distinction is very subtle, but the key takeaway here is that when it's a limit of functions, we can apply L'Hopital's rule. When it's limits of sequences, we cannot apply L'Hopital's rule. So natural log goes to infinity, e to the x goes to infinity. So we can apply L'Hopital's rule, and recall we should always indicate when we do so. So this would be the limit as x approaches infinity, take the derivative in the top, divide it by the bottom. Doing a small bit of manipulation, this would be the limit of 1 over x e to the x. And now as x goes to infinity, we have the bottom going to infinity and the top staying fixed at 1. So 1 divided by something going to infinity gives us back 0 as the limit of the sequence. So once again, in the language that we've introduced, we would say the sequence converges to the number 0.